Good evening to everybody who's here with us for our masterclass. It is my privilege and an honor to welcome Dr. Murli Annavaram and our very respected and beloved provost, Dr. Ravichandran. It's a great honor to have such an exalted faculty around us, and we will be talking about some very keynote aspects for which, Dr. Ravichandran sir, I request you to please take over and introduce our guest of honor for the masterclass.
Thank you. It's a great pleasure to introduce Dr. Murli Annavaram, who is a Dean's Chair Professor in the Electrical and Computer Engineering and Computer Science departments at the University of Southern California, or popularly known as USC. He currently holds the Srimad Rukmini Sri Gopalakrishnachar Visiting Chair Professorship at the Indian Institute of Science. He is the founding director of the Real at USC Meta Center that is focused on research and education in AI, and is the co-principal investigator on the NSF Discover expedition on superconducting computing. His group's night shift research won the 2012 IEEE Micro Top Picks Most Influential Research Paper Award. His work at Intel led to the first 3D microarchitecture design and also influenced Intel's Turbo Boost technology. Murli has co-authored Parallel Computer Organization and Design, a widely used textbook in computer architecture. He has received numerous awards, and of them, I will just note he received the prestigious Career Award from the National Science Foundation. He is a fellow of IEEE and a senior member of ACM. I now invite Dr. Annavaram to present his masterclass.
I'm assuming everybody can see my slides.
Yes, sir, the slides are very visible.
Okay, great.
You can put it in the presentation mode.
It is not. I see. 1 second. Hold on. Is this better now?
Yes, thank you.
Okay. Good afternoon, everybody. Thank you for the introduction. I am pleased to be here. And what I thought I will talk about today is some of the work we have been doing under the Meta Center research, which is the machine learning privacy and security of machine learning systems. And what I wanted to sort of start this presentation is a very simple diagram, which is showing you on this picture here, the knowledge that we all think we know. So these are things that we all, or each one of us has some knowledge about some aspect. So for example, I do research in computer architecture and machine learning. So I consider myself to be reasonably knowledgeable about that topic. And then there's a whole bunch of information that we know that we don't know. So this is basically, let's say, quantum computing. I know what quantum is, but I'm not in a position to do research in that directly. It's not something that I am currently deeply involved in. So this is a knowledge that I know that I don't know. And then comes this huge pie, which is this idea that there is a huge amount of knowledge that we actually don't even know that it exists. And therefore, we don't even know that we actually don't know about this. And so this is a universal problem. I mean, this is a universal truth, but it has very specific implications in digital marketplaces and e-commerce related systems, such as recommendation systems in particular. And so the goal of the recommendation systems, if I were to talk about it at a higher level, is to sort of bring things that we don't even know that exist and show it to us. That's really the goal of the recommendation systems, whether it is e-commerce advertisements, news article recommendations, video recommendations in Netflix. All of these come under this very, very important topic called recommendation systems. So today, what we're going to talk about is a brief introduction to recommendation systems and how they can be used and misused in terms of our privacy violations. And so this is really the focus of the talk. And please interrupt me if you have any questions, and I'm happy to answer them. So let's start with a very simple example. So what I wanted to see is, if I showed this picture to you and I asked you to raise your hand and say, how many of you know what this is? And in general, 80% of the people have no idea what this is. And in fact, when this was shown to me, this was a few years ago, I was also clueless what this particular image was corresponding to. It turns out that image corresponds to basically a flashlight on the back of your bicycle, which can be using a left turn signal, right turn signal, with a remote control attached to your front of your handlebar. And so this is a very, very specific item, or a very specifically designed item. And so you wonder, when I went to, say, an Amazon or a Flipkart website, how does the site know to recommend something so unique and so interestingly different to me? And it turns out that there is a reason why these recommendation systems are able to present this particular object or a particular gadget as a recommendation to me. So here is where it begins. It begins because, let's say Flipkart or Amazon, any of the websites know, for instance, that I am an avid bicyclist, and I have purchased helmets. I have my bicycle, which I also purchased. I have bought bicycle tires. I have bicycle shoes. And so when you see that there is a knowledge built into these recommendation systems that says that these are the items that the user has purchased in the past, then you can kind of see the dots and connect them. And you say, oh, basically this person is willing to spend a substantial amount of their resources. And hence I'm going to recommend something fancier as a bicycle lamp as opposed to a traditional small red blinking light. And so this is an example of what recommendation systems do. And in fact, these are not just unique to Amazon's or Flipkart's or any other e-commerce sites. They existed from a very, very long time. And in fact, when Henry Ford was asked very long time ago, before the introduction of automobiles, and he was asked, so what do you think people would want? And he said, people wanted, if you did not tell them anything, they wanted faster horses. And so you wonder, how come they wanted faster horses? That's because at the time of this introduction of internal combustion engine, horses were most commonly used as transportation mechanisms. And so we didn't even know the presence of internal combustion engine. And as a result, we are not even capable of knowing that such a thing even exists. So that's an example of what we don't know, we don't actually know about it. And therefore, this is where recommendation systems come into play. And similarly, there are other famous quotes that say that a lot of times people... Thank you. Thank you. So the basic goal is to sort of see that this is where all the recommendation systems come into play, and they have been in existence for a long time, but they have become increasingly popular and increasingly critical for the overall benefit of the society, for the e-commerce sites. So let's take a look at what these recommendation systems do. A recommendation system is basically a mechanism to help match users with items. And therefore, when a user logs into a website, you kind of create what items they might actually need or may potentially interact with. And this eases information overload because the people don't need to browse through millions of things, and instead they might be able to just simply get a recommendation of what they are likely to see, and that's what recommendation systems do. So if I were to think of these recommendation systems as an important machine learning model, these are the reason why they're so popular is because these are very, very critical, in fact, for the survival of many traditional e-commerce related companies. For example, 35% of the Amazon's revenue comes from these recommendation models themselves. So what this means is that many of us go into an Amazon not knowing what we want to purchase. You say, type in a t-shirt, I type in a shoe, and then you end up buying what is recommended by the Amazon, rather than you going there and saying, I want a specific model or a sub-model of a shoe that I'm interested in. And so the question, therefore, is these are very, very popular. Sorry, just a second. Okay, so these are very popular. They're used in a wide range of domains, not just in e-commerce. They're used in all other kinds of transportation systems. Many systems use them. And the thing that is very important to recognize, and this is where the connection to machine learning becomes important, is that these recommendation systems today are extensively based on what we call DNNs, or deep neural network-based personalized recommendation systems. And so majority of what these recommendations today are automatically generated through these large machine learning models that run in the back of these large companies. And so what is a recommendation system then? A recommendation system, if you think of it as from a mathematical notion, is a given a set of user models. So basically a user is represented not as in a name, but as some sort of a bit vector representation, which contains their age, their gender, their city location, their potentially their income levels. You combine all of these to create what is called a user model. And then there is a collection of items that are available for the user to potentially interact with. These items could be purchases, these items could be news articles, these items could be videos, any of them could be items. Again, each of these items has a particular item model or item representation. And the goal of the recommendation system is to find a relevance score, which means for a given user, how likely is a particular item going to be relevant? How relevant is each of the items in the system? That's what the goal of the recommendation system is, to find the relevance score for a given user across a whole bunch of items that may be in the collection that the items may be used by the user potentially. So that's what recommendation systems functionally are going to do. So with that sort of background, let me sort of dive a little bit into what recommendation system types are today over time. So if you look at recommendation systems, they were originally started as what is called non-personalized recommendation systems, or also called popularity-based recommendation systems. What does this mean? It means they don't know anything about you as a person, but they may be able to recommend things purely based on the popularity of an item. Let's say that 1,000 people watched a movie. They will say, okay, 1,000 people watched this movie. Maybe there's something important and interesting in this movie. I'm going to recommend it to everybody in the system. So this is what is called a non-personalized recommendation system. The other one is a personalized recommendation system. And in fact, vast majority of although recommendation systems started as a non-personalized systems, they all have moved to become personalized recommendation systems today. And in fact, the majority of the e-commerce as well as social media networks, they all operate out of personalized recommendation models. And so these are personalized recommendations because these are recommendations that are given uniquely to you. So effectively what they're saying is that this model is only generated for you. And the information that I'm giving you, whether a particular recommendation, is only for you as a particular entity or a particular user. And that's why these are called personalized recommendation models. And there are different kinds of personalized recommendation models, which I'll go into in the next minute or so. So this is how the broader categorization of recommendation systems are, both non-personalized and personalized. And within the personalized, there's a whole collection of these recommendation systems are. So let's start with a very simple personalized recommendation system. A simple personalized recommendation system can basically take user profiles, which are basically something about their age, their gender, their income level, their city, and some basic information about the user basically. And then you feed it into this black box, which we call a recommendation engine. And then it produces what is called the relevance score or relevance score for the items. So it's basically going to say that for this particular user who's coming into the system, item I1 has a score of 0.9, I2 has a score of 1, I3 has a score of 0.3, and so on and so forth. So if there are 100 items, you will get 100 relevance scores or relevancy scores. And that way, you know that, let's say in this very simple example, I2 has the highest relevance score of 1, and hence the model is going to tell the user that I2 is more likely interesting to you. This is what recommendation systems do in that personalization aspect. Well, if I can collect information about a user and provide that information, maybe there is something more you can do beyond personalization. So this is what we call the community base. So basically, this is a very famous saying, show me your friends and I'll show you your future. And this is essentially saying that show me your friends and I'll tell you what your next purchase is in this context. And what this is saying is that in addition to the user's information, if you can also bring in the community data. So for example, let's not just look at the user's age and city, but also look at the community of other users with the same age and the same city and the same income level, and see what they also have looked at, whether it is a news article or a particular item purchased, and you feed both the user profile and community data to these recommendation components. And then the model then generates a list of items and their personalization scores for that particular user. And so now this information that is generated is not only from the user's information, but also from the community of people. The community could be, it's not necessarily your friends that you're thinking about. These could be just people who are the same sort of bin or category of people that are in your same profile category. So this is what we call the community-based recommendations. And then there is something else that is also popular, which is, this is a very interesting quote that says, you are what you buy. And so these are basically self-driven recommendation systems. And what does that mean? What it means is the following. You take the user profile and you take a selection of products that the user has purchased. These are basically self-driven because it is based on the user and their past interactions with the system. So I say, hey, I am a user X, and I have purchased a particular shoe or a particular t-shirt, and I feed both of those and then get a recommendation score from that black box recommendation model that is there. So these are basically what is called self-driven recommendations are based on product user combination recommendation models. So these are sort of the three, sort of broadly speaking, personalized recommendation systems that people have developed over the years. But obviously, this is not enough in current large social media networks, social networks, or e-commerce sites, and they need something more than what these recommendation systems can do. And so I usually say this slide for in-person attendance for students. I'm not sure how many of you are from South India. Sambar is a very popular South Indian item. And essentially, when you cook sambar in particular parts of the South, you basically put everything in your kitchen into the sambar and boil it over, right? And so this is basically the idea that when you put multiple ingredients together, something interesting is going to pop out of it. And therefore, people take this exact sambar equivalent concept to recommendation models. And now you have everything that we talked about, which is user profiles, community data, product features, knowledge models, all of it goes into the recommendation model. And then you will end up with basically what I call a sambar equivalent of the large recommendation system. And that's where we are, in fact, today. Vast majority of the recommendation models fall in this category where you throw everything excepting the kitchen sink into the problem and you generate a recommendation from them. And you wonder, is it really going to be useful to put so much data into it and so much stuff into this black box? And it turns out that actually works surprisingly well. So these models actually, when they take a lot of this information and they throw everything into this pot, it actually works relatively well. And so what are these models going to look like? The way you can think of is let me kind of jump into, before I talk about how these models are actually these large complex models are going to be used, let me talk about very simple. Let's start with how these models can be trained in a very simplistic sense. Let's take a look at a very simple example I have. Let's say that we have 5 movies, item 1, 2, 3, 4, 5. This could be movie 1, 2, 3, 4, 5. And Alice has given a rating of 5 to item 1, a rating of 3 to movie 2, and 4 to movie 3, and another 4 to movie 4. And now the system is thinking, oh, this is a movie 5 that I have. I want to know what is Alice's likelihood of watching this movie. That's really the goal. And so the goal is, what is the likely score that Alice is going to give to this movie 5? That's what we want to understand. And so there are different ways of solving this problem. The one way to solving this problem, as I said, is based on community information. And the community information is shown in this data where user 1, user 2, user 3, and user 4 have already rated all the 5 movies as shown in this particular matrix. Given this information, the goal is to find what is the likelihood of Alice liking this particular movie 5. So how do we do this? The way to do this is to find the user who is the most similar to Alice. And what does that mean? We're going to compute similarity scores of Alice with each of the users. And so we say Alice has a similarity with user 1 of 0.85, has a similarity of some other number with user 2, user 3, user 4. So you now have a notion of how close Alice is with respect to the other users in the system. And once you know what the users are in the system and how similar they are to Alice, it's now easy to see that of all the users, Alice is closest to user 1, and user 1 has recommended or has rated the movie 5 to be number 3, and therefore one could say that Alice is likely to rate the same movie as number 3. And that's basically what is called the community-based mechanism of learning. And this is based on user similarity, or basically community information that is captured in these systems. Now, if you were to look at alternative strategies, an alternative strategy is called item-based collaborative filtering. And the idea here is that instead of looking at similarity of Alice with other users, let's look at the similarity of items across each other. And so this is what is called if I bought item 1, item 2, item 3, and item 4, what is the likelihood of I'm going to buy item 5? This is sort of the similarity across items that we're going to be interested in. So here now we're going to look at the similarity not in the row by row information, but across columns we're going to look at the similarity. So what you see here is that item 1 is similar. So you're looking at item 1 similarity with item 5, item 2 similarity with item 5, item 3 similarity with item 5, and so on and so forth. And basically looking at this, we say that, oh, the item 5, the closest item to item 5 means probably item 4 in this simple example. And therefore, what I can say is that Alice has rated this particular movie to be rank number 4, or a classification of 4. And therefore, for movie 5, which is closest to movie 4, it's likely that Alice is going to do a rating of 4. This is again a prediction based on the similarity scores across columns. So this is another way of producing the scores of missing items, and this is what is called collaborative filtering, also very popular for many years in recommendation systems. Hopefully this is clear until now. If there are any questions, please speak up, otherwise I'll continue. All right. If none, I'm going to go to the next slide, which is to say, if you look at these very simple recommendation systems, now let's take a deeper look at more complex recommendation models. And so the complex recommendation models are the ones which I was talking about, which is the idea of throwing everything into the kitchen, from the kitchen sink into the pot, and figuring out if they work well. And so what we have here are recommendation models, which are the latest type of recommendation models, which use a collection of features which are called continuous or dense features, as well as categorical features. And I'll go into details a little bit in just a minute, but these are the two sets of features that are actually used by current recommendation systems. So to kind of give you a deeper understanding of this, let's take a look at a simple exemplary architecture of a recommendation model. This is a a recommendation model that is very similar to the DIN or the DIEN recommendation systems from Alibaba. And it is also very, very similar to TLRM from Meta, wide and deep recommendation systems from Google. These are the examples of recommendation models that look a lot like this. So I thought I'd take this example and kind of drive home the actual recommendation model architecture of today's systems. So what these systems do is that they can take something called a dense features. The dense features, for example, could be a user's city, for example, could be a dense feature, or the income of a user could be a dense feature. So there are certain classes of information that are there, which we call dense features, and it doesn't matter what is dense and what is sparse. It is decided by each company. So some companies may treat age as a dense feature. Some companies may treat the user's age as a sparse feature. So you can have two different kinds of features in these systems. So you have a dense feature and a sparse feature. And what does the sparse features do? And this is where most of the magic of recommendation systems goes into. These are called sparse features, or what are called embedding representations. Let me give you an example. An example of an embedding representation and why embedding tables are so important is the following. If I say clothes and shoes, most of us as humans can relate to them and say, oh, they're kind of related, because people who buy shoes and clothes many times together. And so we as humans over time have captured that knowledge that shoes and clothes are related to each other. Similarly, if I told you ASICS and Bata, you might also know that, oh, this is kind of the same kind of idea that ASICS is a brand of shoe, Bata is a brand of shoe. But to teach that knowledge to a computer model is actually where the challenge is. You have to tell, in this very simple example, I can just say that these are related and I tell them directly. But imagine learning these relationships automatically. And that automatic relationship detection is what these embedding tables do. And what they do is, let's just take the example of Bata and ASICS as the two kinds of brands of shoes. Initially, they are represented as a bit vector. Bata is represented as a random bit vector of zeros and ones. And the ASICS is another random bit vector of zeros and ones. And that bit vectors could be thousands of bits wide. And this is what is called an embedding associated with the Bata and embedding associated with ASICS. Now that we know what is the embedding associated with Bata and ASICS, these are random values. Now, every time a user buys ASICS and Bata shoes together, you take those random vectors and you bring them closer to each other. That is the goal. You can bring them closer to each other when they are related. And what that means is that the embedding tables are learning that these two items are similar, have some commonality, by basically taking these big vector representations and moving them closer to each other. So instead of having some random values for zeros and ones, maybe the Bata will have 0, 0, 1, 1, 1, 0, and the ASICS may have 0, 0, 1, 1, 0, 0. Instead of 0, 1, it may have 0, 0. So you can see that bit vectors look very similar in this multidimensional space, and that is what embedding tables do. And vast majority of these models, whether it is the DIN model, DLRM model, wide and deep model from Google, have these embedding tables, which are the heart and soul of these recommendation models. And the big difference is what is inside these tables. Like some of them may have category, brand, and interactions. Some other company may have age and gender and other kinds of things in their embedding tables. But fundamentally, the architecture looks this way. Now, with this architecture in mind, now how does one get recommendations? Imagine that now we have trained this system. How does one actually get a recommendation out of this system? The way one gets recommendation out of this system is as follows. Take a look at this 3 histories of past user interactions from user 1. So user 1 had interacted with the system 3 times in the past. And the first time they purchased they favorited something from category 7, let's say it's clothing, brand 12, let's say this is Raymond's. And so they say that item 7, category 7, brand 12, and they have favorited it. They haven't purchased it, they favorited that brand of clothing from Raymond's, and they said, this is my favorite. The second interaction that the user had has category 5 and brand 15. Let's again say that this category 5 is a shoe, a brand in this case is, let's say, Asics. And they bought this. And so now you have a user with a category 5, which is a shoe, a brand, which is Asics, and they bought it. And the third interaction is same, category 2, brand 1. So this could be, let's say, some other like glasses, like sunglasses from Ray-Ban. And so you bought this, or you put it into the cart, you did not buy it. These are the 3 interactions you had with this system in the past. Given that you had these 3 interactions you had with the system in the past, the goal of the recommendation model is to find out which of these categories, brands, they should recommend to you on the 4th time you visited their website. That's the goal of the recommendation model. And this is what is called the inference or a recommendation, where your past history of interactions are provided as input. Based on the past history of inputs, it will predict what is likelihood of you getting a new item or a brand and purchasing it. That's the goal of these large-scale recommendation models. Hopefully that is clear. And with that introduction and understanding of recommendation models, I thought I will spend the next, I don't know, however many minutes we have, maybe about 25 minutes or so, or to 15 minutes or so, because I want to leave some time for the questions on privacy aspects of these models. So in the past slides that I showed you, it is clear to every one of us that you have to interact with this system and tell the system, I have used, I have purchased an ASIC shoe, I have used or I have favorited a Raymond shirt, and therefore I have given some information about me to this system. And as a result, what is the implications of this information being given to the system in terms of our privacy or in terms of our data itself being captured? That's the goal of the next part of what I wanted to present. And so the goal, therefore, is what are the privacy implications of using the recommendation models? So before I go there, let me just sort of highlight one more thing here, which is that when I say category 7, brand 12, and favorite, all they are is nothing but their indices into these large vectors of tables. So category 7 simply says that this is entry number 7, brand 12. It says this is entry number 12 of the brand table. And therefore, you are essentially providing indices into these tables. And what I wanted to highlight and specifically point out to you is that I only have indices into this table, but not the actual data itself. For example, the data here may be completely hidden from me. I don't actually know what is the data in that system, but I simply know that I have accessed category 7 and brand 12. This is the information I have. And so I'm going to make this very simplistic, the assumption is so simplistic that I assume that I know nothing more than just I accessed entry 5, entry 12, entry 7, entry 4. That's all. If I know this information, what kinds of potential privacy losses that we see? This is an important goal of what we wanted to talk about next. So let's take a look at what exactly is going to be the loss in these systems. And so the idea, therefore, is you're going to see some privacy loss, which I'll show you. And if I show you that there's privacy losses in this system, you want to say, why does this matter? Like the loss of privacy. There are multiple reasons why this matters. For large companies, whether it is the Amazons or the Facebooks or any large e-commerce websites, not only e-commerce, even just a regular physical mortar and brick houses, they are going to be bounded by privacy laws. If you are familiar with European GDPR laws, they are very strict about sharing what data you can use and collect about a user. Then there's also growing demand from users themselves. The users no longer are interested in giving all the information, and they also want to know what is being done to the information the system collects. And so we are going to be interested in privacy because of privacy loss, demand from the users, and at the same time, one can say, well, I don't want to use recommendation systems. That's not practical. For those of you who have been to a Netflix or one of the Amazon Prime, you will see there are literally thousands and thousands of videos, and there is no way you're going to browse through this the 1 minute trailers for these thousands of videos before deciding what you're going to watch. So you do need these recommendations to help you. And so you're kind of in this bind where you have this privacy laws, there's a demand from the users, and you still want to enable commercial use of these recommendation models. And so that's the goal. That's what we were interested in doing. And hence, the next few things that I want to show you is that given these concerns, what I want to share with you is what are the kinds of attacks that one can do by just gaining accesses to the table indices. Remember the number 7, number 12, number 5. This is all I have. What can I learn from these things? And I want to show you that there are 3 things that can be done or can be extracted by an attacker by gaining the knowledge of table accesses. When I say table, I mean the embedding tables, the brand, the category, and such. One is called the identification attack, which basically identifies you potentially as the one and only one individual. Second, sensitive attribute attack. This is the second type of attack where you can potentially retrieve information about a user that the user has not given that information to you. For example, you can retrieve a user's age. Without knowing anything about the user's age, you can accurately predict what the user's age is. So that's what is called sensitive attribute attack. The third one is called re-identification attack. These are the attacks where a user can be re-identified in the system just using their past recent interactions in the system. So this is actually very powerful because I don't even log into Amazon or into these various websites. I will just simply be able to identify the user just when they come to my website without knowing who they are, without knowing their login or passwords or anything of that nature. So these are the 3 attacks that I'm going to demonstrate to you are feasible in current settings. All right, so let's take a look at these 3 attacks within the context of what I call data sets. We started with, this is work that was done in conjunction with several of my students and some of my collaborators at Facebook and Meta. So we started with this data set called the Taobao ads display data set. What this is showing you is this very, very large data set that is provided by Alibaba that has the following information about the users. They have information about the users called the micro group ID, gender, age, city level, and shopping depth. These are the features associated with a user for a given user ID. So the user ID is in the purpose of this data set, it's a sort of a random number that is given. So we don't know who that particular user is, but we have the user ID. So given this information, what we wanted to see in this very large data set containing millions of records of interaction histories a user may have, how likely is it that if I don't show you the user ID, but I showed you these features or some subset of these features about the user, can you guess who the user is? That's the goal. That's what we are interested in. All right, so let's take a look at, is it feasible or not? So if I don't give you the user ID, and if the user can be one of 97 group IDs, micro group IDs, 13 group IDs, one of the 2 genders, one of 7 ages, one of 4 city levels, one of 3 shopping depths. And therefore, if you don't have any information, it is likely that the total number of possible choices that the user may belong to is 97 times 13 times 2 times 7 times 4 times 3. And so you can only say, if you have no other information, that the user is one of 211,000 buckets, which is the multiplication of these numbers that are shown here. So the total bins a user can be there is 211,848. We say, okay, this is good. We don't know who the user is other than is one of 211 possibilities, 11,000 possibilities. But the reality is quite different. The total number of bins in the data set is nowhere close to 211,000, but instead it is much closer to just 1,000. And that is actually striking. When we saw this data, we were really surprised that how can it be that the number of users can be placed into a total of 1,100 bins, not 211,000 bins. A little bit of a further analysis showed that there are certain interactions or certain combination of these features that don't exist at all. And what does that mean? Let's just take a simple example of a gender. And this is true in this particular data set. It is observed in this data set that wedding gowns are interacted with by users typically in the age group of 25 to 35 from female gender and from a particular city level. So, for example, a relatively large or a medium-sized city. And so, if I look at the combination of wedding gowns and villages and women, zero. There are zero of that combination. If I look at the wedding gowns, medium-sized town, and male, there are zero such entries. So if you can see, even though the total number of bins are very many, possible bins are many, the reality is that the number of bins in the actual data set is extraordinarily small. And this is even more striking. The more striking information is that the number of bins with just one user is just 56. So these are the bins where if I combine the microgroup ID, the group ID, the user gender, and the city depth and all of that, some combinations, there's only one user in the entire system containing millions and millions of records. And so this is what I call the loner syndrome. Basically, this is where you are essentially one of the few people who interact with the system from that particular category. And therefore, you are the one person in the system. And hence, if I gave you some combination of this information, and if that combination of information is unique, you can uniquely identify that user ID. And in the case of this 56, there are 56 such combinations. There's only one user, and I know the user with no ambiguity at all. For students who have taken any course in data sciences, you may have heard the word data anonymity, which is basically what is called k-anonymity, which is telling you the probability of me identifying a user with a probability of 1 over. It's the identification of a user with 1 over k probability. One anonymity, for example, is the user is identified with no ambiguity. Two anonymity means the user is identified as one of the other one is one of two people. Basically, there are 154 categories where there are only two individuals. So I don't know who the precise individual is, but I know one of the two individuals, and so on and so forth. And this is what is called the k-anonymity data that you can see. It's striking in terms of how many times there are very few people in this system. Then the next attack that I wanted to show you is the sensitive attribute attack. So, we are all technologists. We say that we are very good about recognizing our privacy losses. And I'm going to create a cloak around me, a privacy cloak around me. And what does that mean? It means such as recommendation systems such as IMDb actually don't require you to enter any profile information. You just create your user ID and you say nothing about your age, your gender, your city, none of it. You say nothing about you. And even more interestingly, a user can actually provide inaccurate information too. So if I'm really intelligent, I'll say, oh, I am going to say that my age is 70. I am from a small town, not from Los Angeles. And I will just simply say that this is my profile. And so the goal is if a user has given no information or provided inaccurate or incorrect information, is it still possible for me to peel that profile clock and identify that user and see what that user looks like? And I want to show you that it is in fact possible. The reason it is possible is shown in this very simple illustrative example. If you look at this picture, it is showing you that there are 5 categories of items, Legoland, Disney, Apple, Oculus, and Christian Dior, and the age group of people interacting with each of these items. And in this particular example, the age group of people are talking to Oculus, are interacting with Oculus. Oculus, I'm sure many of you know, is basically this VR headset. I just had the lab tour of your facility. And in that facility, I saw that some of you were actually using these kinds of VR systems. And so you see that if you are interacting with this Oculus VR, it turns out that 100% of the users are from this particular age group 5. And again, I'm just illustrating it to drive home the point. Don't take this exact number to mean something. Given that, let's say that I am a user who is going to be profile cloaked, and I access Oculus in this system, in this particular model. The moment I access Oculus, I did not say which age group I am, but with a very, very high probability, I can say that the user's age is in the group 5 category because majority of other users who have accessed the Oculus came from age group 5. This is what I mean by the friend syndrome. Essentially, you can be de-anonymized because you decided to protect yourself, but your friend decided not to protect themselves. And as a result, because they have disclosed their age and they accessed Oculus, you did not disclose your age, but you accessed Oculus. You can create these cross correlations across age groups and automatically identify the age group of a user without the user telling you what that age group is. And so this is what we call the ambiguity score. And so, for example, in Oculus, I know the age of a student, of a person with a 100% likelihood, and there are close to 100%, and therefore I have 0% ambiguity. So we created what is called an ambiguity score. An ambiguity score is basically what is the likelihood that I don't know what the user's specific feature is. And so the ambiguity score for users with respect to Oculus is age has a 0% ambiguity. And in the case of Christian Dior, there is a 40% ambiguity because we will say that there may be 60% from age group 7 and 40% from age group 4. And so therefore the ambiguity is 40%. And so that's what we can say, that these are the ambiguity scores of these users, of these features. And now let's go back to the data set and see what are the ambiguity levels of these data sets. So I plotted on this the ambiguity about an age group using brand information. And so what I see here is that 25 of the brands are actually used by a single group of users, age group of users. And therefore, there is no ambiguity in predicting the age of the group because they all come from a single age group when they access one of these 25 brands in this particular data set. And in fact, 50% of the brands are accessed by a majority of age group, which means that if you look at a particular brand, that brand is accessed by people from an age group, let's say 3, 50% of the people, or more than 50% of the people are from age group 3. And therefore, I know with a very high likelihood what your age group is if you access that particular brand. And so this is really striking because half of the brands have a very strong correlation with the age group. And therefore, it's not like you have to access a particular brand. If you access one of the million brands, you still have a very high probability of getting disclosed with respect to your age. Gender is even worse, right? In terms of the ambiguity scores, 80% of the brands have 20% ambiguity. And what that means is that if I look at if you access a brand, majority of the people who access that brand are either male or female. And therefore, and it's not just a simple majority, it's 80% majority, which is like a very strong absolute, or like is a strong majority of the people accessing these brands come with a very low, either male or female, and therefore very low ambiguity in these systems. And hence, even if you decided to not say whether you are what your gender is, these systems can extract that information by just simply looking at the brands and what other people who have disclosed their gender and kind of cross-correlating that information back to you. And the last attack that I have about 5 minutes I want to talk about. It's called the re-identification attack. There's a lot of text, but I want to sort of leave these slides for you, and I'm happy to share these slides with you a little bit later on. And Malvika can forward the slides to you. The idea here is very simple. I'm going to set up the stage here. The setup the stage is I am on this laptop. I do not log into a website, whether it is Flipkart or any of the e-commerce sites. And I provide them, I want to know a recommendation. I want to know what is it that is in their catalog that will be of interest to me. So I give them the last 2 things that I purchased from them. And I don't say who I am. I simply say I purchased item X and item Y, and that's all I'm going to tell you. And then I close my laptop. I go to a desktop in your office. I have never been to Geo Institute before. This is the first time I'm coming, and therefore I'll go to one of your desktops in your lab. And I go to the same website and I say, hey, I purchased item X and item Y, give me a recommendation. That's what I'm going to tell the system. And it turns out that if I tell the system that I purchased item X and item Y from this laptop and from a desktop where I have never logged in, the system knows with a very, very high probability that this person who purchased item X and Y from the laptop is exactly the same person who is now at Geo Institute and purchasing and wanting a recommendation, because these items X and Y that I purchased are so unique that the 2 recent purchases can give you an identification with 98% certainty. That's actually another striking result, which means that in the entire system, there are no 2 individuals who purchase the same 2 items within the same window of time. I forgot to say that it's a window of time. Let's say that I said I purchased item X on day 1, item Y in day 2. That's really all I'm going to say. And so it turns out that the users can be easily identified if you give me the last 2 recent purchases. And therefore, if you can give me the last 2 purchases that you have, and I will tell you who you are with an extraordinarily high accuracy. And the conundrum here is that you do need to disclose these last few transactions for you to get a good recommendation. And if you don't have this, if you don't disclose this, you're not going to get good recommendations. And so one might actually step back and say, how is it possible that there are 98% likelihood? Think about it. When you have 1 million movies in Netflix or on Amazon Prime or any of these other sites, the chances of 2 people watching or purchasing the 2 movies in the same sequence within a short window is exceedingly small. These are basic probabilities, right? If there are 1 million things, what's the probability that I pick one in that? 1 in a million. What's the probability I pick another 1 in 1 million? Now you combine them, it's extraordinarily low probability that there is somebody else which has the same 2 sequence of items. And hence, it looks striking and stunning. And when I presented this information to many of the companies, they initially were stunned, but they realized that this is actually quite common. It's in fact true. It's just that in hindsight, it becomes obvious. And once you start to think about it, it becomes really, really problematic. And so in the next slide, which is kind of the last of my slides, I wanted to show you that if I present the threshold hours, which is by x-axis, what I'm showing you is that if I am tracking what the user purchased today and 250 hours later, so in a 10-day window, 2 purchases in this 10-day window, and I can see that as I look at 250 hours, which is almost 11 plus days window, the precision is 98%. And if I only look at a small window, let's say that I say that who has purchased these 2 items within a window of, let's say, 10 hours. It turns out that if I'm looking at the purchasing of 2 items with a precision within a short window of 10 hours, you are identified with 100% accuracy. So there's no ambiguity in who that purchases are, because the probability of somebody else purchasing the same sequence of items decreases when you have a short window. So if you increase the window, it slowly, the probability decreases, but the precision is still not like substantially lower. You went from 100% to 99.5%, 99%, 98%, 98.5 and 98%. So you effectively, by the time you get to 250 hours, you still have a lot of information about you that is stored in the system. So with that, what I wanted to show you is that recommendation models are ubiquitous. Every user of a recommendation system is vulnerable to privacy. And the information leakage comes not from data, but just by accessing the indexing table information itself, which is a very small amount of information. So what I wanted to, this is an important assumption, because what I wanted to see is, I don't want to know much about it. I want to know very little about it, and I still can I get extra information about it. And that's exactly what I showed you, is that by simply identifying very simple indices to these tables, I can get a lot of information extracted from the user. And protecting the data access patterns is critical for these systems, and hence I believe that there's a substantial amount of research that is necessary to work on data protection, data privacy, and user privacy in these systems. And in fact, a lot of the centers that I work with, I run a couple of large machine learning centers. Our goal is to actually kind of figure out a way to reduce the information leakage in these systems in an efficient manner. So with that, I will stop here. I want to thank you for listening in for almost an hour, and I want to say stay private.
Thank you so much, Dr. Murli. It was a pleasure listening to you, and a lot of new things did come up, which I think will be an eye-opener for all of us and for all our listeners. Thank you so much for your very, very informative words. I now request Dr. Nilay to please conclude this session for us. So please do share your thoughts and views.
Yeah, if there are any questions before that.
Yes, sir. So we will come to that. So I request you to please share your concluding remarks.
All right. Thank you, Malvika. And thank you so much, Dr. Murli. It's been a very informative session. And on behalf of Geo Institute Executive Education, we are very grateful to you for sharing your insights. One of the things which I think it works both ways is that while we are browsing, or we are even trying to understand how these recommendations happening, and somebody is watching us behind the scene, we too can actually understand behavior of people who are likely to hack us. And if that, using deep learning systems, so it can also be used by people who are from the security agencies to help identify who are possible hackers, who are likelihood of possible hackers, how they will operate, how will the next attack happen. Just now in the afternoon, I was discussing with one of our colleagues, and he was telling me about how one of the leading global organizations in data science, how they are actually able to predict a very, very private matter of an individual just by browsing. It's a medical matter. How that organization could actually spot and predict a medical issue of a person just by understanding how the search history, the browsing history. Because their research has found that when a certain medical situation happens, some chemicals are released in the body, which in turn affects your search behavior and browsing behavior. And there was a kind of a correlation. So such is the power of such deep learning systems. Many times we don't even see the connection or correlation, but something is happening behind the scenes. So on the one side, we have to be very alert, of course, but on the other side, it's fascinating to see how such technologies and how such how the world is moving. So thank you so much, Dr. Murli, once again, and Executive Education of Geo Institute frequently conducts such programs, for the general audience as well as for corporate audiences as well. And I would invite you to constantly look at our websites, constantly visit our social networking sites to know more about such programs as and when we hold it. Thank you so much to all the participants for joining us today. Thank you.
Thank you so much, sir. That was indeed very helpful. I now open the session for questions and answers. One of the first questions that we have here is that what is the overload on security systems if they are implemented on deep learning systems? So how will the security systems react? Are there chances of an overload? Dr. Murli,
yeah. Yeah, so if I understand the correct question correctly, the question I think is that if I were to protect the privacy and security, what is the cost in terms of how heavily the systems will need to be computing additionally? And it turns out that's a good question. If I understand the question, and if that is the question, it's actually a very good question. And it turns out that protecting privacy in this particular context, at a high level, I'll give you an example. Imagine that you, instead of telling the system that you purchased an item 1, you tell the system that I purchased item 1, 2, 3, 4, 5, 6. It kind of overload the system with hundreds and hundreds of random data in addition to what you purchased. And then you still will get some recommendation, but not necessarily the accurate recommendation. But this is costly because you're sending huge amounts of data to the system and then let the data be churned through the recommendation model, which is mostly spurious data. But that can protect you, but it is very expensive. Typically today, the access costs will typically be, in the order of about 100x. And so that's a substantial cost. And therefore, the current practical systems that do this kind of protection are very expensive. And there is, in fact, that's the reason why there's a substantial need for research in these systems.
Thank you so much.
Thank you. That question was from Anurag Sinha, I think. Yes, and Anurag, thank you for your question, Anurag. Thank you for joining us today. Incidentally, Dr. Murli, Anurag is a very good friend of mine, my classmate, and currently a very senior person with TCS. So, yeah, thank you, Anurag.
So there is another question which says that how do you sanitize RS from subjective knowledge? And this, I think, the person who's asked you this question is Dhiren Patel, and he wants you to maybe ponder over points a little away from the privacy theme.
Again, if I understand the question correctly, I think the recommendation models from subjective logic in the sense that to some degree, if I interpret this is something about biases in the system and how biases can come into play in these systems. And it turns out that removing, this is a completely different topic, as you rightly pointed out. It's not a privacy issue. It's actually an issue of fairness and lacking biases and kind of removing these biases in the systems. And it turns out that that's also equally difficult, if not even more challenging than privacy. And it has something to do with the fact that your recommendation models are trained with data that's already somewhat biased. And therefore, your system is overall sort of biased in some ways. And in fact, that's the bias actually is what is actually exploited in our system's privacy. For example, if when I said wedding gowns as an example, and in the models that we studied, I said vast majority of the interactions with the wedding gowns came from a particular gender. And again, that's a gender bias that kind of embedded in the system, and it sort of permeates through the system. And in this particular example that I gave you, it may not be very harmful, but you can clearly see that there are certain scenarios where these biases can have substantial direct effect, both in the society and also in the person's interaction with the system itself.
Thank you so much, sir. There is another question which is basically aimed at asking that how does artificial intelligence enable recommendation systems? How do they help us bring in an ethical policy on privacy from companies?
Yeah, it's a good question. In fact, there are, the privacy always is a combination of technology and policy, right? It's no longer just simply technology or policy. If you look at policy decisions, policy has always lagged technology, particularly in digital world, because the digital world moves at such a rapid pace that policy cannot move at that pace. And whenever the policy decisions are made, they're already outdated because the digital world has moved on in terms of what the technologies are. And as a result, the goal of any future policy decisions has to be in conjunction with the technologists. And so, in fact, there are lots of interesting, I'm not as familiar with the Indian governmental policies, but at least in the US, some of these privacy protection forums have actually close collaboration with researchers in technology side. I mean, these are people who know nothing about legalese. They don't understand. They're not lawyers. They're not legal people, but they understand technology very well. And when you draft these policies, public policy and computing are now, actually, there are some schools. For example, Princeton has a school that combines public policy with technology to show that these are actually interesting interactions that occur in these systems. And so, so I think it's not a simple answer as, oh, this can be done. I think it's a very complex matter that in fact requires these two groups of people to collaborate and communicate, collaborate in a open forum so that this policy and technology sort of evolve together. Otherwise, one can prohibit the other from making progress.
Thank you so much. That was very informative. And I hope that everybody who asked those questions is now happy with the answers, because as I said, your words are very profound and they've opened an entire new insight into this very exciting field. So thank you so much for your very valuable time. Thank you to all our panelists who took out the time to be with us for this session. And thank you to all the attendees. It was great having you. And I really hope to see you in some of our future masterclasses as well. Thank you so much for all your participation and for all the efforts, sir. Dr. Murli, thank you. We wish you all the very best. Thank you so much, Dr. Ravichandran. Thank you so much, Dr. Nile. It was great hosting you all for this session. Thank you and good evening.
Thank you. Thank you, Dr. Murli.